My dear student, today let us discuss about Fatou's lemma, very fundamental in measure theory. Using this theorem, we will be, proving lots of important theorems. So this is very fundamental lemma. Fatou's lemma. Name of the theorem is Fatou's lemma, and this is the statement. So what the statement says is that Fn is a sequence of non-negative measurable function. It is a sequence of non-negative measurable function. Then, so the conclusion of the theorem says that limit infimum, integration Fn dx is greater than or equal to limit infimum Fn dx. Okay, so this is a function. Limit infimum Fn x, it is a function. Integration of this function, it is bounded by this number, this real number. So what is the left-hand side is, for every n you integrate it with respect to x, you get a real number. So you have a sequence of real number. For that sequence of real number, you find out limit infimum. Okay, that value is greater than or equal to integration of this function. Okay, limit infimum Fn is a function, but here limit infimum is just limit infimum of a sequence of real number. Okay, so this is all about the statement of the theorem. All right, so yeah, so limit infimum definition I already explained in the previous classes. I assume that you understand it. Whenever you have some confusion or something, misunderstanding, you can talk to me. Okay, so limit infimum Fn is a function. That function is denoted by f. Let us denote it by f. Then in the earlier theorem we have proved that, so if Fn is a sequence of non-negative measurable function, then the limit infimum function f is also measurable. Therefore f is a non-negative measurable function. Okay, also we know that how you define integration of a function. Integration of a function is defined by this formula: supremum of all such integral where phi is a simple non-negative simple measurable function which is dominated by the function f. That means phi is less than equal to f. So you think about all those simple measurable function which is less than or equal to f. You take integration of all and such simple measurable function. So the supremum of such simple measurable function integration, okay, is the integration of the function f. All right, so that is the definition of integration of a non-negative measurable function. Okay, so then it is sufficient to prove that if you are able to prove this inequality, number one, if you are able to prove this inequality for all such simple measurable function which is dominated by f. Okay, so if you are able to prove that integration phi dx is less than or equal to limit infimum integration Fn dx for all phi which is less than or equal to f, okay, then it is done. The theorem is over, because so supremum of this side, this is less than or equal to this one. Okay, so how many such phi are there? There are lots of phi. There are lots of phi which is less than or equal to f. Okay, so think about all those phi, then think about the integral of all those phi. You have different values. Those different values is dominated by this real number. Okay, dominated by this one. Then if you take the supremum also, it will be dominated by this one. So if you take the supremum, what do you get? If you take the supremum, what do you get? You get integration f dx. Okay, you get integration f dx. What is f? F is limit infimum Fn. All right, then it is done. So what is the important thing you have to remember? If you are able to show this inequality, number one, then it is done. Okay, the theorem is over. So let us prove this inequality. Okay, So in this inequality for all non-negative simple measurable function phi such that phi is less than equal to f. All right, so let us divide into two cases. Case number one, if the integration of the simple function is is exactly equal to infinity. Okay, so what we have to do, we have to do this, inequality. We are going to prove this one. So in proving this one, there may be some cases where integration of phi dx is equal to infinity. Okay, so that is the case number one. Integration phi dx is equal to infinity. So by the definition of simple measurable function integral, so this is equal to what? Summation I running from 1 to n ai measure ai. Okay, so these ai's are non-negative, and measure is also non-negative. This finite sum is equal to infinity. That means what? You have product of two non-negative real number, you sum up to n times, that is equal to infinity, means what? One of the term must be infinity. Okay, that means these ai's are finite, this cannot be infinity. That means this measure ai must be infinity for some term. Okay, so what is the conclusion you have to draw from this equality is that there must be some measurable, okay, set a whose measure is equal to infinity, and on all points of a, so this phi is non-zero, means phi is strictly greater than some positive number. Okay, all right, so if you multiply by that positive number to infinity, the result is infinity. So therefore we should be able to find a measurable set a whose measure is equal to infinity. So at all points of a, phi is strictly greater than some positive real number a. Okay, so this is the conclusion you can draw from this equality. Summation I running from 1 to n ai measure ai is equal to infinity. All right, so that is what. So what is you have to you have to take, there exists some measurable set a whose measure is equal to infinity, and there exists some non-negative real number a such that phi is greater than a on a. Okay, so then let us write gkx is equal to, say, infimum j is greater than or equal to k fjx. So this infimum. All right, so then I'll tell you this gk is an increasing function. Okay, you have a sequence of set g1 g2 g3 g4 for a particular value of x, g1x g2x g3x. Okay, you have sequence now, that is monotonic increasing also. So that is straightforward from the definition of infimum function that we have already talked about last time. So you define gkx like this, infimum this one. You define gkx infimum this. All right, so then let us see something then, yeah, so that it will be very clear later on. You have a sequence of function. You have a sequence of function fi. So this is a sequence of function. So then what is gk? Gk is equal to, at a point x, gk is equal to infimum j is greater than or equal to k f j x. So this is gk. So that means g1 x is less than or equal to g2 x. You have a sequence now, g3 x goes on. Okay, so that means gk, new function, sequence of function gk, it is monotonic increasing sequence of function. Okay, so then if you take supremum here, what happened? Supremum over k running from 1 to infinity. So then you have to take supremum here, supremum over k is running from 1 to infinity. So supremum k infimum j greater than k, this is equal to what? This is by definition, this is limit infimum fn x. All right, this function. So this function we put how much? This function we put it is equal to f. This function is equal to f. All right. So supremum gkx is equal to supremum k infimum j running from k to infinity. Okay, f of x. So this is from definition is equal to how much? Limit infimum fn. But limit infimum fn we put f. Okay. So again, we are going to take supremum k. You are going to take supremum k. That means 1k running from 1 to infinity. Then you have to you have to take supremum of, say, suppose you have at gx1 g2 x2 and goes on. You have sequence of real number, right? And this sequence of real number is increasing. That means g1x is less than equal to g2x2. This is x. Okay, same x. All right, then gx like this increasing. All right, so since it is increasing, supremum will happen when k tends to infinity. All right, so supremum will happen when k tends to infinity. Means what? This supremum is equal to how much? Then this supremum is equal to limit k tends to infinity gk. All right, so what is the thing you have to remember? Since this gk new sequence of function is monotonic increasing, and supremum gkx is equal to is nothing but limit k tends to infinity gk. All right, for a function for a point x. So limit k tends to infinity gkx, because why? This is monotonic increasing sequence of function. Okay, so that is the thing you have to remember, keep in mind. Then let us go back to the note. All right, so now you define gk like this. Gk is equal to infimum j running j is greater than equal to k fj x. Then let us define an again. So an is equal to x such that gk x is greater than, for all k greater than equal to n. All right, then since gk is measurable function, this an is also measurable function. Measurable set. Okay, an is measurable set. So then and then it is obvious that an is subset of an plus 1. Why an is a subset of an plus 1? Let us see. Also this one also I will explain it. What is an? An is equal to, this is x such that gk x is greater than a for all k greater than equal to n. All right, so that means what? Then what is an plus 1? An plus 1 is equal to x such that gk x is strictly greater than a for all k greater than equal to n plus 1. This is your n plus 1. Okay, so if a point x is a member of n, then this is true. G kx for all gkx is greater than a for k all greater than equal to n. Then it is true for k n plus 1 also, n plus 2 also, n plus 3 also. It is true, na? So that means whenever x is member of this one, and x is also member of n plus 1, because why? Gk n plus 1 x is greater than n a, n plus 1 greater than x is greater than a. All right, so that is quite clear from the definition of an and an plus 1. So what is the thing you have to remember? This an plus 1 is a superset of this n. So an, then you have a sequence, this sequence, this is monotonic increasing sequence of measurable set, and n is also measurable. Okay, n is measurable because why gk is measurable. All right, so an is a subset of n plus 1. You have a sequence of measurable increasing sets. All right, so then let us go back to the note again. This is true. Yeah, whatever I have told you, it is written here again. N is a subset of n plus 1. It is also clear that for each x, this is a monotonic increasing sequence of real number. Therefore, so whatever I have told you, therefore what, supremum infimum fj, j is running from k, j is greater than or equal to k, fjx is equal to supremum k x, but this is equal to limit k tends to infinity gkx, because why, g is monotonic increasing. So that is this is what, this is f of x. F of x means what, according to the definition, limit limit infimum f n x is f of x. So this is equal to this f of x. Okay, so that is what we get it. That means from here what you get, limit k tends to infinity gkx is equal to f of x, but f of x is always greater than or equal to phi of x, but phi x is greater than a, right? Phi x is greater than a. So therefore x is a member of capital A implies that gkx is greater than a for all, for some k, for all k greater than or equal to n. Okay, right? After some stage, when k is greater than or equal to n, all right, because this limit k tends to infinity gkx is equal to f of x, but this f of x is greater than or equal to phi x, and phi x a. So whenever x is a member of a, so this is true, all right? So whenever x is a member of a, this is true, and a is greater than 0 now, this is true, but this quantity is dominated by f of x, but f of x is equal to this one. So after some stage is gk, after some stage is gkx is going to be greater than a, okay, because limit this is equal to this one. All right, so the stage is when n, when k is equal to n and greater than n, then in that situation gk x is going to be strictly greater than this small a. Okay, so gk x is greater than a, all right, for all k greater than or equal to n. So it follows that, you know, x is member of an, all right? So according to the definition of an, if gkx is greater than a for all k greater than or equal to n, then this x is going to be a member of what, an, all right? So what does it say? It says that whenever you take one element from a, that is going to be member of some an. That means what, this a is going to be subset of this union, countable union, and going from 1 to infinity an, all right? So you have a sequence of set which is monotonic increasing. That means a1 is subset of a2 is subset of a3, like this. You have a sequence of such measurable set. In their union, a set a is also member, you know, in their union a set a is there, okay, it contains, all right, the set a whose measure is infinity. Therefore measure of this one is going to be infinity, right? The set a has measure infinity and it is a subset of this union. Therefore this union is going to be, you know, its measure is going to be infinity. But what is, you know, measure of this union? This is, you know, we already did this theorem. This is equal to limit n tends to infinity measure an. When n tends to infinity measure an, that is equal to this, exactly this one, all right? So what does it say? Since this is going to be infinity, limit n tends to infinity measure an is going to be infinity, right? So this, you get it, this one. Okay, now from our construction, you know, from our construction, fn is going to be greater than or equal to gn. So let me explain it, why it happens. Yeah, fn, what is g? What is g? G is equal to gkx, gkx is equal to infimum, you know, j is greater than or equal to k f j x, all right? So infimum, you are taking infimum, so infimum will be less than every member of the, you know, you are taking from j starting from k na, jk plus 1, jk plus 2, jk plus 3, starting from k onward you have a sequence of functions like jk plus 1, jk plus 2, like this. So you take infimum, the minimum one, the minimum will be less than every member of the sequence, no? So that means what, that means what, a member, suppose let us consider this member, this f of kx is also member. Now starting from k, this is a member. This is going to be greater than what, the infimum one, the infimum, the smallest one, then gk x. All right, a problem start again. Yeah, now it's okay. So it is going to be greater than gkx. Okay, so if k is equal to n, then f of n x is greater than or equal to g of n x. This is true. So every f n x is greater than or equal to g n x. This is true. All right, so that is why we get this one. So this function is greater than or equal to this function, therefore by the property, integral of this function is greater than or equal to integral of this function. So you get this one, this integral. But integration gn dx is greater than measure man. So this is quite obvious, because what, gnx is g at an, what you have at a set an, gnx is greater than a. All right, so its integration is going to be gnx, this integration is going to be greater than this one. Okay, this is true. All right, so that means what, but this is true for all n, but as n tends to infinity, but this quantity is going to be infinity. All right, this we have already done. As n tends to infinity, this quantity is going to be infinity. So as n tends to infinity, this is going to be greater than infinity. So the only thing is that it is exactly equal to infinity. All right, so you have f1 integration dx, that is also going to be greater than infinity. F1 2, so no, you have a sequence of such real number, integration f1 dx, integration f2 dx, integration f3 dx, like this. Okay, so therefore limit infimum fn dx is going to be infinity when n tends to infinity. So limit infimum, so n tends to infinity, this is going to be limit infimum. So therefore this quantity is going to be infinity. All right, so that is what you have. So then the first case is over. Why the first case is over, let me tell you. When this is when this first case is when this is infinity, this is also infinity. So infinity is equal to infinity. So this equality is here, that is true. Okay, so the case 1 is over. What we want to show, we want to show the first inequality number 1. So this is true when integration phi dx is equal to infinity. Okay, so that is what we have done. And next, next, so then what have you have this inequality. Okay, so then case 2, let us take case 2. Case 2 is the case when integration of phi is finite, less than infinity. So in this case, let us write b is equal to x such that phi x is non-zero. Okay, non-negative. Phi x is strictly greater than 0. Okay, so it follows that since this is this is not infinity, it is finite, so then measure of b must be finite. Okay, measure of b must be finite, because I already explained you, this is sum of I running from 1 to n ai measure, say bi in this case. So you define b is equal to like this, x such that phi x is strictly greater than 0. Right. So from here what you have, since it is finite, so measure cannot be infinity, no? Measure cannot be infinity. So then phi can take only finite values, say a1, a2, a3 up to an. Right. So out of this a1, a2 up to an, so m, let us take that m is the largest value of phi. So m is the largest value of phi. So then you define Bn is equal to define Bn is equal to such that x such that gkx is strictly greater than, you know, phi x. It will have some value, then 1 minus epsilon for some arbitrary small epsilon. This is real number, so this is x such that gkx is greater than this one. This right hand side is real number for all k greater than or equal to n. Okay, then what, since gk is measurable, this bn is also measurable, so you define bn like this, and bn is measurable set. Okay, so where epsilon is a very small number, less than 1, greater than 0, and gkx as we define above is equal to infimum j greater than or equal to k fjx. So gkx as we define, so this is monotonic increasing sequence of, you know, measurable function. Also likewise in an, bn is a subset of n plus 1 for all n is greater than or equal to 1. So what we have a sequence of measurable function bn which is increasing. Okay, and b, what, b is going to be a subset of a this union. B is going to be subset of this union, because why, phi x is, you know, when phi x is non-zero and epsilon is very small number less than 1, so this is non-zero. Okay, so this is non-zero. That means what, at the point of bn the function gkx is going to be non-zero. Okay, so what is b? B is where, you know, phi x is non-zero now. So if phi x is non-zero, your gkx is going to be non-zero. Right, that means what, this b is going to be subset of n going from 1 to infinity bn. All right, so this is easy, you can do it. You can, you know, whatever I explained to you, you just write it down and do yourself. Okay, then you will understand more. All right, so there is no magic trick to understand mathematics very quickly. The only thing is that you give attention to what I explain and then try to write it down by your own using pen and paper. That is the only way to understand mathematics. Okay, so then this is, and then again this is you know, is a decreasing sequence. I'm telling you this is a monotonic decreasing sequence. Means what, b difference b1 is a superset of b difference b2 like this. Okay, and b difference b2 is a superset of b difference b3, so it is decreasing, no? Is a decreasing, you can prove that one easily, you do it also. Is a decreasing sequence of sets and they are all measurable such that, you know, this is infinity. Why this is equal to phi? Because your b is a subset of this union, no? So that means whatever in b, it will be in some bn. Okay, so you are taking out each bn in each step now. So after some steps all the b will be taken out, you know, from b, so their intersection is going to be empty. All right, intersection n going from 1 to infinity b difference bn is empty. So that means again by the result we did earlier, measure of b is finite. So therefore, you know, limit n tends to infinity, measure of b, bn is equal to limit of this intersection, and the limit, you know, measure of this intersection, but this intersection is equal to phi, so it is 0. Okay, that means what, limit n tends to infinity m b difference bn is equal to 0. So again by the definition of limit, there exists some positive integer capital N such that measure b difference bn is strictly less than epsilon for all n greater than or equal to capital N. All right, measure b difference bn is strictly less than epsilon for all n greater than equal to n, because why, this limit is tending toward 0 now. So this is true for some arbitrary small number. We should be able to find a positive integer n such that for all n greater than equal to capital N, this inequality is true. Okay, so that is from the definition of limit. Now again, so here the integration is on whole the set of real number R, and Bn is a subset of R. Therefore, by that theorem we did earlier, integration g, this is greater than or equal to this one. Okay, because the domain is different. Here it is whole R, here it is a subset Bn of R. All right, so that means what? So this integration gn dx is going to be greater than integration gn dx and domain on the set Bn. So again, gn is greater than 1 minus epsilon phi, right, in the set Bn. All right, so therefore this is true. Gn is greater than 1 minus phi, okay, on the set Bn. So you can replace it like this, gn by phi, and then you will get this one. So now what you have b is equal to what? Disjoint union of these two set, b difference bn union bn, a disjoint union. Okay, so therefore again by the theorem we did earlier, measure integration over the set b is equal to integration over the set b difference bn integration over the set bn. Okay, so that means what? If you want to find out this term, then you get this. All right, so from here what do you get? So then integration gn dx is greater than equal to this quantity. Okay, because this quantity has been replaced by this one. All right, so then you get this equality. So that means what? So this is small number less than 1. All right, this is a small number. Okay, so so then a small number, then if you take out a small number, this quantity is going to be bigger, right? This quantity is going to be bigger if you take out 1 minus epsilon. So you have taken out a bigger quantity. That means this whole quantity is going to be less than this one. Okay, so the earlier, that's this one. This is quite obvious. Then what happened? Then this is going to be, now again from here phi is dominated by m. M is the largest value phi can take now. So from here again the bigger one is taken out. Okay, so that means the bigger, so this is phi is replaced by m, then this integration is equal to m times measure of this one, this set b difference bn. So since m is bigger than phi, you are subtracting the bigger number. That means this whole quantity is less than this one. Okay, so this is equal to, now again this is going to be greater than, this, after this one you get this one. All right, you get epsilon m, but epsilon is arbitrary. Epsilon can be very, very small number. So since epsilon is arbitrary, we have what? So integration g n dx is going to be greater than phi dx. This is true for all n greater than or equal to capital N. All right, so that means what? Since g is monotonic increasing as n tends to infinity, what you get? So limit infimum, you take limit infimum is going to be the, as n tends to infinity. So this is going to be, limit infimum is going to be greater than phi dx. All right, but since fn is greater than equal to gn, so then its integration is going to be greater than gn. So yeah, this integration gn is going to be less than here, fn integration. So the result follows. Let me explain in the window then you will understand. Let me explain here what I mean. For every n, fn x is greater than or equal to gn x. So this implies that what? This implies the integration fn dx is going to be greater than or equal to integration gn dx. Alright, so if you put limit infimum here, the inequality doesn't change. Fn dx is going to be greater than or equal to limit infimum gn dx. Alright, so but this one is greater than what? So that the result follows. This is greater than what we have here, phi dx. Okay, phi dx. So that is inequality number 1. Okay, the inequality number 1 holds. Okay, so if I have already explained you, if inequality number 1 holds, okay, the theorem is done. So we have divided into two cases. When integration phi dx is equal to infinity, in that case inequality number 1 holds. Okay, so when integration phi dx is finite, inequality number 1 also holds. Okay, so then the theorem is over. Alright, so as I told you earlier, if you have some confusion, don't forget to call me. Okay, that is the only way to learn. Alright, you practice yourself. Whenever you have confusion, you have to consult your teacher. Okay, so anyway, thank you very much.